They existed before the dinosaurs, survived multiple mass extinctions, reshaped ecosystems, and silently rewrote the history of life on Earth. Yet most of us have never noticed them. The origin of worms, ancient survivors of Earth's earliest ecosystems. When we picture the story of life on Earth, our minds jump to the giant reptiles of the Mesozoic, the armored trilobites of the Paleozoic, or even the enigmatic creatures of the Cambrian Explosion. But long before the thunderous footsteps of dinosaurs or the strange creeping of trilobites, the planet was already inhabited by organisms whose evolutionary roots stretch back hundreds of millions, perhaps more than 1 billion years. These creatures were the worms, humble, soft-bodied animals that quietly etched their presence into sediments, ecosystems, and ultimately, the evolutionary map of life. Today, we explore their origins, not just to understand worms themselves, but to uncover how their existence reshaped Earth's early biosphere, diversified ecosystems, and influenced the very architecture of animal evolution. Chapter 1. What exactly is a worm? Before we trace their lineage, we must address a surprisingly difficult question. What is a worm? Biologists will quickly note that worm is not a scientific classification. It does not refer to a single phylum, lineage, or evolutionary branch. Instead, the term refers to a body plan, elongated, soft, flexible, vermiform. Earthworms, leeches, velvet worms, tapeworms, roundworms, and flatworms are not close relatives. They belong to separate evolutionary branches that diverged hundreds of millions of years ago. Yet, despite their distance, evolution repeatedly arrived at the same solution: a long tubular body optimized for burrowing, feeding, and survival. This phenomenon, multiple unrelated organisms evolving similar forms, is known as convergent evolution. And in the case of worms, convergence happened early, repeatedly, and with extraordinary ecological success. Chapter 2. Worms before the Cambrian. To find the earliest worm-like organisms, we travel back more than 500 million years into the Ediacaran Period, a time dominated by soft-bodied, enigmatic creatures that confound paleontologists to this day. Among these early organisms was Dickinsonia, a flattened, ribbed animal that sprawled across microbial mats. Though not a worm by strict modern standards, its simple bilateral form resembles that seen in later vermiform groups. More compelling is the small organism Eukarya, recently interpreted as an early bilaterian capable of controlled movement. Though only millimeters long, its morphology places it near the base of the animal tree, possibly representing one of the earliest worm-like ancestors. These Ediacaran worms were not dominant, but they were pioneers. They burrowed, wriggled, grazed, and most importantly, they moved, using their bodies to disturb sediments and reshape the seafloor, marking an early shift in biological engineering known as the agronomic revolution. Chapter 3. The Cambrian Explosion and the Rise of Worm Diversity. Fast forward to the Cambrian Explosion, roughly 541 million years ago, where life diversified at an unprecedented pace. The seas teemed with bizarre forms, some armored, others spined, many experimental. Among these fantastical creatures was Hallucigenia, a whimsical-looking animal with spines on its back and grasping limbs below. Today, we know Hallucigenia as a relative of modern velvet worms, members of the phylum Onychophora. While not a worm in the traditional sense, its vermiform body plan underscores just how ancient worm-like forms truly are. The Cambrian also gifted us other important groups, including the first confidently identifiable annelids, the segmented worms. Chapter 4. The Annelids. Segmented survivors. Annelids are among the most recognizable worm groups today. They include earthworms, bristleworms, and leeches, and their origins trace back over 508 million years to the famed Burgess Shale deposits of Canada. Here, paleontologists uncovered species such as Canadia sp. with distinct bristles called Burgessakita. Another polychaete showcasing early segmentation. These fossils reveal that annelids were already specialized, segmented, and ecologically diverse early in the Cambrian. But the most extraordinary annelid discovery came much later. Dinosaurs, described in 2018. Exceptionally preserved, it displayed soft tissues including potential neural and vascular structures, offering unprecedented insights into how annelids assembled their bodies. Most notably, its head featured bristles extending from generalized segments, evidence that annelid heads evolved from posterior body regions through specialized developmental modification. rather than emerging as a distinct ancestral feature. This single fossil changed how biologists modeled annelid development, merging paleontology with evo-devo research. Chapter 5. Before the Cambrian. A possible surprise until recently, scientists believed annelids were confined to the Cambrian. But discoveries challenged this. Fossils such as Phragmacheta, found in lower Cambrian strata in Greenland, pushed annelids earlier and earlier. Then came Eulingia, dating between 551 and 539 million years ago, potentially predating the Cambrian explosion. This elongated, segmented animal left clear trace trails, indicating decision-based locomotion, a profound leap in behavioral complexity. Whether Eulingia represents a true annelid, a stem arthropod, or a related bilaterian is debated. But one thing is clear: complex worms roamed the seafloor before the Cambrian explosion, suggesting the event was less of an instantaneous explosion and more of an ecological amplification. Chapter 6. Nematodes. The ubiquitous worms. If annelids take the prize for structural elegance, nematodes or roundworms win for sheer numbers. With an estimated 40,000 species, and likely many more undiscovered, nematodes inhabit nearly every environment on Earth. Soil, deep-sea vents, freshwater systems, Arctic ice, and even the internal tissues of animals, including humans. A 2019 global study estimated 4.4 times 10 superscript 2 nematodes in the world's topsoil, a number so large it defies comprehension. But their origins are ancient. While soft bodies rarely fossilize, paleontologists found nematode body fossils from Devonian Scotland, roughly 396 million years old, preserved within the tissues of primitive vascular plants. Even older evidence appears in Ordovician sediments from China, tiny cylindrical burrows left behind by worm-like organisms. These push nematodes back to at least 470 million years ago, with some specialists proposing nematodes might trace back over 1 billion years. Such longevity makes nematodes one of the oldest and most successful worm lineages to ever exist. Chapter 7. More worms in the fossil record beyond the major groups. Other worm-like phyla enrich the fossil story. Priapulids, humorously nicknamed penis worms, flourished during the Cambrian, burrowing, scavenging, and predating within marine sediments. The Burgess shale genus Atoya remains a classic example, showcasing feeding structures and digestive contents. Meanwhile, stem onychophorans like Hallucigenia underscore how worm-like bodies gave rise to later legged taxa. These transitional forms remind us that worms were not evolutionary dead ends. They were stepping stones. Chapter 8. Ecological impact and survival. What makes worms extraordinary is not simply their age, but their resilience. Worms survived multiple extinction events, shifting continents, fluctuating climates, and atmospheric upheavals. Their impacts include bioturbation, burrowing oxygenated sediments and reshaped microbial environments, nutrient cycling, accelerating decomposition and soil formation, parasitism, altering food webs and evolutionary arms race to symbiosis, cooperating with plants and microbes, ecosystem engineering, transforming marine and terrestrial landscapes. In short, worms were architects of Earth's early biosphere. Chapter 9. Conclusion. The unsung architects of life. From Ediacaran mats to Cambrian seas, from Paleozoic forests to modern soils, worms endured. They thrived not through size, armor, or ferocity, but through simplicity. Their tubular bodies proved evolutionarily adaptable, their strategies efficient, and their ecological roles indispensable. In studying worms, we uncover not just a branch of life's history, but a foundation. For the story of life on Earth is not merely the tale of giants. It is often the story of the small, the soft, and the overlooked. If this journey through deep time reshaped how you think about worms, there is much more to discover. Because in the grand narrative of evolution, even the humblest of organisms carry chapters capable of rewriting our understanding of the past. Subscribe, share, and explore further. The world is richer than it seems beneath our feet.